Okay, this is gas lesson 3. We're going to do Boyle's Law, Charles' Law, and Gay-Lussac's Law. So first off, Boyle's Law. This is Boyle's Law. It's a formula where pressure and volume vary inversely. So P1 V1 equals P2 V2. So this is the only one where the volume varies inversely with only pressure. That's Boyle's Law. So that means and the temperature is held constant, and as the pressure of the gas increases, the volume decreases. That's what inverse means, okay? So what inverse means is as one variable goes one way, the other variable goes the opposite way. So if pressure goes up, volume goes down. And the reverse is also true. As pressure decreases, then volume increases. Okay? So that's Boyle's Law. It's the inverse law. The rest of them aren't inverse. That's the only one. Okay? The rest of them, they have various things going on. Okay, so let's turn the page and do an example. Okay, so here is a picture of kind of how Boyle's Law works. So this is what you call a piston, this little thing here with a handle on it, and the piston can slide in and out of the cylinder. So think of like a syringe. A syringe has a piston that goes in and out, and as the piston goes into the syringe or cylinder, then the volume is decreased. So if the volume decreases, you're compressing the gas particles in a smaller space, which means they collide with each other in the walls of the container more often. So increase in collisions means an increase in pressure. So as the volume goes down, the pressure goes up. And the opposite is also true. So if the piston were to go back up, then the volume would increase, giving the particles more space, so there would be less collisions. Less collisions means less pressure. Okay, so here we go, Boyle's Law. So it says we have a balloon containing 30 liters of helium gas at 103 kilopascals. What is the volume of the helium when the balloon rises to an altitude where the pressure is only 25 kilopascals? All right, so in this case, we have a V and a P, and we're looking for a V and a P. So our only variables are going to be P1, V1, P2, and V2. So line up your variables in the left-hand margin. So this is V1 is liters, so 30.0 liters. That's the initial volume. And then the initial pressure at that volume is 103 kPa. Okay? And then we're looking for the new volume when the pressure is decreased to 25.0 kPa. Okay, so the pressure is going from about 100 to 25. So the pressure is decreasing down to 1/4 of what it was. So what's the inverse of 1/4? It's about 4. 4 over 1, 4. Which means for our pressure to decrease that much, our volume must go up the inverse of the amount. So it should go up to about 4 times of what it was. So our answer for volume should be around 120 liters. So, okay, so let's see. So P1 V1 equals P2 V2. We're looking for V2, so we're going to divide both sides by P2. Okay, so when we do that, we just plug it in. So 103 kPa times 30.0 liters over 25.0 kPa. So kPa's cancel and you're left with liters. Okay, so then we stick that in our calculator. Okay, and so our numbers all have 3 sig figs, so our answer should have 3 sig figs. That's about 124 liters. That's pretty close to 120 liters, so that's the correct answer. Okay, moving on, Charles' Law. Okay, so Charles was a hot air balloonist, and what he figured out was that as you increase the temperature of the air inside the balloon itself expands. So what Charles' law is actually saying is as temperature increases, the volume increases as well. So as temperature of an enclosed gas increases, the volume increases. Okay, and the pressure is held constant for this one. That's why there's no pressure in the equation. So this is a direct proportion. Okay, so Charles' law is saying that the volume is directly proportional to the temperature. Okay, as long as the pressure is held constant. Okay, so remember, Charles, he's the hot air balloonist, right? So that's why he decided, oh, well, let's investigate volume and temperature. That's why. Okay, so kind of remember that if you're trying to think about Charles' law. All right. So using Charles' law. So we have a balloon inflated to a room at 24 degrees Celsius. Ooh, we don't like degrees Celsius, do we? No. So we're going to stick that in our calculator, right? So 24 plus 273.15, and that gives us 297.15 kelvins. Okay, and it has a volume of this, 4.0 liters. The balloon is then heated to a temperature of 58 degrees Celsius. Ooh, we don't like that either. Okay, so 58 plus 273.15, and we get 331.15. Okay. Okay, what is the new volume if the pressure remains constant? Okay, so in this case, we have a V1, a T1, a V2, and a T2. And that's all we've got because there's no pressure, so there's no pressure change, there's no R value, because this is an initial and a final. You can only use the ideal gas law if there's no initial and final, only one set of conditions. So our V1 is 4.00 liters. Our T1 in kelvins is 297.15 kelvins. Just remember, though, that that was 2 sig figs before we stuck it in here. Our V2 is what we're looking for, and our T2 is 331.15 kelvins. And again, that was 2 sig figs before we used the actual Kelvin temperature. All right, so V1 T2 equals V2 T1. So if we're looking for V2, I'm going to divide both sides by T1. Okay, so now we plug and chug. So 4.00 liters times 331.15 kelvins over 297.15 kelvins. Notice that our kelvins cancel and we're left with liters, which is what volume should be in. Now we just stick that guy in our calculator. Okay. Okay, and our original numbers, we have 3 sig figs, 2 sig figs, and 2 sig figs. So 2 sig figs wins, so this ends up being 4.5 liters. Okay, all right, so that's Charles' law. And Gay-Lussac's law. Okay, so Gay-Lussac's law is pressure and temperature vary directly while keeping the volume constant. So this would be in what you call a rigid container because the volume can't change. So we only vary pressure and temperature. So it says as the temperature of an enclosed gas increases, the pressure increases. And so we're keeping the volume constant. Okay, so how is the volume constant? It's in a rigid container. Okay, so when a gas is heated at constant volume, the pressure increases. So Gay-Lussac's law states that the pressure of a gas is directly proportional to the Kelvin temperature. Okay, and that's assuming that the volume remains constant. Okay, so they're using an example of a pressure cooker. So inside of a pressure cooker is a very rigid container, and as the temperature increases, that means the average kinetic energy of the particles increases. So if the particles move faster, then that means you have more collisions more often with the walls of the container. Well, that's what pressure is. So if the pressure increases while the volume remains constant and the temperature is increasing, that's what Gay-Lussac's law is describing. Okay. All right. So let's look at our example problem. So it says, using Gay-Lussac's law, aerosol cans carry warnings on their labels that say not to incinerate or burn them or store the cans above a certain temperature. This problem shows why it's dangerous to dispose of aerosol cans in a fire. Don't ever do that while you're camping. That's stupid. The gas in a used aerosol can has a pressure of 103 kilopascals at 25 degrees Celsius. We don't like Celsius, right? So that temperature is actually 298.15 kelvins. If the can is thrown onto a fire, what will the pressure be when the temperature reaches 928 degrees Celsius? So we're looking for the new pressure when we have this temperature, but we don't like that temperature, right? So 928 plus 273.15, can't do that in my head. So that temperature is actually 1201.15 kelvins. Okay, so we have an initial pressure and an initial temperature, and we have a final pressure and a final temperature. So those are our variables lined up in the left-hand margin. Okay, so P1 is 103 kilopascals. Okay, and then our T1 is 298.15 kelvins. Our P2 is what we're looking for, and our T2 is 1201.15 kelvins, because whoever throws cans into a fire is relatively stupid. So P1 T2 equals P2 T1. We're looking for P2, so we're going to divide both sides by T1. Okay, so now we just plug and chug. 103 kPa times 1201.15 kelvins over 298.15 kelvins. Kelvins cancel, you're left with kPas, which is what pressure should be in. And now we just stick it in the calculator. So 103, can't see that, there we go, maybe, times 1201.15 divided by 298.15. All right. Now, originally, this was 2 sig figs. Right? That's 3 sig figs, and originally this was 3 sig figs. So between 3, 2, and 3, 2 wins. So our answer is to 2 sig figs. Now we have to round that number to 2 sig figs. So that's approximately 415, but that would be 3 sig figs. So what do? Right? It's 414 and then 9, blah, blah, blah. So see, you have to round that 1. So we would round it up if the number after was 5 or higher. But the number after is only 4. So we're going to round this down. So this is 410 kPa. If you think of it like money, you can't screw the sig figs up. Okay? So if I owed you this amount of money and you said round it to 2 sig figs and pay me on Friday, I would owe you $410. I would not owe you $41. Okay? I would owe you $410. Okay? All right, and that's the end of gas lesson 3.